Okay, everybody, here we are. Day 2 of polar graphing. Gonna take it up a notch. Today we're gonna take a look at what are called limacons or limacons, depending on your French pronunciation. Some people just say limacons, whatever you like. But a polar graph that is what's called a limacon is anything that's of this form. R equals a plus or minus some constant b times sine of theta or cosine of theta. Yesterday we were looking at if it was just r equals b sine of theta, that would be a circle symmetric with the y-axis, and if it was just b cosine of theta, symmetric with the x-axis, but again a circle. Now what happens when we add a constant to that? So one way to go about these is always just plug in some points, connect the dots as best you can, and if you're good at plotting polar coordinates, it's not too bad. So let's take a look. Let's try this one, 3 minus 3 sine of theta, just by plugging in some points. We'll do some quadrantal ones, but we'll try a couple in between too. So 0, pi over 2, pi, 3 pi over 2, 2 pi. If you like, maybe this is dealing with sine, so maybe I'll use the pi over 6's because that gives you out 1/2, a rational answer, as opposed to pi over 4 or pi over 3, which will give you root 2 over 2, root 3 over 2. So, of course, you can always plot those if you want to see, a fuller picture. So I'll try the 5 pi over 6, 7 pi over 6, 11 pi over 6. Let's see, this should give us a pretty good picture. So if I plug in 0 into this equation for theta, I'm going to get sine of 0, 0, and 3 minus 0 is 3. Pi over 6, sine of pi over 6 is 1/2. 3 times 1/2 is 1.5, and 3 minus 1.5 is 1.5, or 3/2. Pi over 2, sine of that is 1, so 3 minus 3, 0. 5 pi over 6, also going to give you positive 1/2, so minus 1.5, so 3 minus 1.5 is 1.5. Plugging in pi, we get 0, so we get 3. Let's try some of these. 7 pi over 6, because sine of 7 pi over 6 you will get negative 1/2, and so negative 1/2 times negative 3 is positive 1.5, so 3 plus 1.5 will actually give you 4.5. So there's a new value there. 3 pi over 2 will give you negative 1 times negative 3 is positive 3, 3 plus 3, 6. 11 pi over 6, again, we're going to get the negative 1/2, so that's going to give us 4.5, and 2 pi is going to give you 0, 3. Now, even this might not be enough. We might need to plug in more, but this is giving us a good variety of points. So let's see. 3 comma 0, so that's right over here. 1, 2, 3. R equals 3, theta 0. 1.5 pi over 6, so as we're rotating along to pi over 6, now our r is shrinking to 1.5. So do your best to plot that point. Pi over 2 as we continue rotating, but r is now 0. So remember, whenever r is 0, we're right here at the origin or at the pole. 5 pi over 6, r is 1.5. So as you continue rotating, now you're rotating to 5 pi over 6, your r is back to being 1.5. And then pi, r is 3. So we're continuing rotating, we're right there. 7 pi over 6, you can view this as you sort of rotating around the circle. It's a sequence. We have r is 4.5, so r has actually gotten a little bit bigger as we rotate out here. So 7 pi over 6, 4.5 will put you right about there. 3 pi over 2, r is 6, so that's going to be down here. 1, 2, 3, 4, 5, 6. Sorry, lost count there. 11 pi over 6, 4.5, so that's 11 pi over 6. 1, 2, 3, 4 and a half. And back to this spot right here. And that is actually giving us all we need to graph this. And I'm just going to graph it in red just for the fun of it, so that you can see when you graph this. Hey, I said you were going to love this problem, and what we got here, it kind of resembles a heart. It kind of looks more like an apple to me. but this type of limacon is called a cardioid, when it has that heart shape, that little cusp right there. So a cardioid, you're going to find, is one type of limacon, and that's when the A and the B value are the same, or at least the absolute value of them, 3 and 3, ignoring any positives or negatives. And you're going to hopefully see why in a minute. But one cool application, if you want to look up any further about this, is if you're into like sound engineering, or might be down the road, a lot of microphones are based off of polar graphs. And there's a thing called a cardioid microphone that if you place the microphone right here, it's programmed to sort of block out sound behind it, but to just capture in the immediate area and out in front of it. So that's a pretty common kind of microphone. They also have kinds that are, designed to be more slim and just straightforward and backward, and those are all polar graphs too, called shotgun microphones. But it's all based on polar graphs, so it's actually a pretty cool application. Well, let's just take a look at one more of these for this video, and then I'm going to break it up and do side 2. But the question here is there a better way to do this than just plugging in points? And I say maybe, because that's kind of up to you. One way is plug in some points and have at it, and that works just fine. The other way is what I touched on a little bit yesterday with these, and that's to think of this, to tie this to the sinusoidal graph. So r equals 2 plus 2 cosine of theta. I'm just going to think about this as y equals 2 plus 2 cosine of x. And even if you don't end up using this technique to draw the graph, I still think it's nice, because if nothing else, it reviews your sinusoidal traits back from chapter 4. So who knows if we'll ever have a final exam, but it's good to know this stuff. So this graph here, the period is 2 pi. I haven't changed that at all. That would be a constant on the inside. The amplitude is 2, but now that I've added 2, the midline is 2. So that's actually going to be shifted up 2 units. So now the middle of the graph is going to be right there. Our period is 2 pi. So our nice normal stretch, or our increment as we called it in class, is still every half pi. And this is a positive cosine graph. Positive cosine is going to start at the peak, or above the midline by that amplitude of 2. So this is going to go as high as 4. And if you didn't know, of course, you would just plug in 0 to get yourself started. But if you remember, if you're really good with these graphs, you know that the next key point will be right on that midline. The next key point will be below the midline by 2, which will put you at 0. The next key point will be back on the midline, and then back above it. And you have this. And what you've really done, if you sketch these in a hurry, is it's like filling out a table, because you have all these points really right in front of you. So now, instead of the y-axis, just keep in mind that with polar, I'm letting r stand in place of y. So these values here are your r values, and of course your angle, which is your x-axis, these are really your theta values. So let's take a look at this here. This first point is theta is 0 and r is 4. So r is 4, theta is 0. 1, 2, 3, 4. That would be starting right there. And then if you think about this as you are rotating to pi over 2 on the polar graph, so as your angle increases from 0 to pi over 2, your r value decreases to 2. So as we go to pi over 2, our r value is now 2. Then as we continue to increase our angle to pi, our r value is 0. We're down here just touching the x-axis, so that's going to put us right at the origin, or at the pole, anytime r is 0. And then 3 pi over 2, r increases back out to a value of 2. So 3 pi over 2, 2 will put you right there. And then 2 pi, you're back to having an r value of 4, which puts you right back here. And if you kind of can just follow the flow of this, what's happening is as you're going from this point to this point, I use a little color here to correspond. From there to there, that's corresponding to here to there. So as our R value increased, or actually decreased as our theta value increased, we were going from there to there. As you were rotating out, our R value was decreasing. So as we were rotating in that positive direction, our R value was decreasing. So you can see it. It's kind of as you rotate, your R value is kind of shrinking at the same time. So you're rotating and shrinking. And then what happened is from here to there, you can probably just fill in the dots, but it's kind of nice to break it down. Between here and there, what happened is we continued rotating. Our R value was decreasing as our theta value was increasing. So what happened is it got pulled right towards that origin, and then it's getting reeled back out again. Then our R value is increasing as we continue to rotate. So we're getting like that. And then this last portion of the graph, we just continued rotating and our R value continued to increase. So you got another one of these polar apples, or cardioids as they're called. But notice, it's a cardioid, but this one was symmetric with the x-axis because it was a cosine cardioid, whereas this one was symmetric with the y-axis because it was a sine cardioid. And just to hit this up again, of course, you can always go to Desmos and type this in if you got a graphing calculator. Also kind of cool, remember I said yesterday, the thing I like about the graphing calculator, even though the graphics aren't as good, but you can watch it draw it as the angle rotates. So I kind of like that, whereas Desmos just throws the graph right at you. You can see the graph developing. And so when we hit graph, wow, isn't that an exciting graph? How about we zoom in and get a little bit better picture of that? There, a little bit better here. You could really set your windows, clearly if you want to adjust that. And if you want to see it graph it again. Yeah. Anyway, pretty cool. You can turn the trace on and you can watch it as you turn to the right. As it increases your theta, you can watch it rotate. And here you go. Very nice. So what's causing it to just glance off of that origin, to get to the origin or the pole and then sort of bounce right back off, is the fact that this is just glancing off the x-axis when R is 0 just for that moment, and then it's getting reeled back out. So that's what's happening there. Okay, we're going to see what happens when that's not the case in our next video, which is the back side of this worksheet.